So to use partial fraction decomposition technique to break up this rational function, what I need to do is I needed to factor the denominator. I noticed there was a GCF of x, so I factored that out. And then what I noticed left is this looks like a quadratic equation, or quadratic function, polynomial. So x squared times x squared is x to the fourth, and 1 times 1 is 1. So that's how that factors. It's a polynomial in quadratic form. It's a quadratic form polynomial. And then because these are like terms, I just squared it. I wrote x times x squared. So that's the denominator factored. And then what you got to think about is I'm going to be able to write my decomposed fraction with an x in the denominator, and then because I've got repeated quadratic factors, that's a quadratic factor that will not factor any further. The way you deal with those repeated factors, just like repeated linear factors, is I'm going to write the x squared plus 1, and then I was going to put parentheses on that, but I don't need to. And then you do it, the x squared plus 1 squared. And if I add it to the third power, I'd have to do that again. And then if it's a linear factor, I can just stick an a up, because it's 1 power or less. This is like a times x to the 0. It's 1 power less than your denominator. So that same deal here, it's going to be bx to the first plus some constant, and then this will be another dx to the first plus a different constant, or maybe it's the same, we don't know, but it looks something like that. Okay, so I've got that broken out. Now what I'm going to do is on this right hand side, the side that I just made, I am going to clear the denominator. In fact, I can even clear this side by multiply both sides of this equation by that common denominator, and that's what I forced it to be. So I did this out on paper before, and I didn't want to rewrite it all here. So what I did is I multiplied what each of these fractions needed for that common denominator. So this is a over x. Well, it needs the x squared plus 1. So that's why I wrote a times x squared plus 1 squared, because this whole fraction was, if I multiply by that common denominator, the x would cancel out, but the x squared, make sure you understand what I'm talking about here. I'm going to multiply this whole fraction by x times x squared plus 1 squared. Okay, so that would be, in that case, that x and that x, because I'm going to distribute this through each one of these terms. That x and that x cancels out, so that leaves me a times the x squared plus 1 squared. And then the second fraction would cancel out one of those x squareds, or one of the x squared plus 1, but it still would have the x and the x squared plus 1, then times that numerator. And then for this last one, the x squared plus 1 squared cancels out, but I'm left with x. That's why I wrote x times what that numerator is. And then I expanded this by foiling, or multiplying two binomials. Got that. I distributed the x through to get the x cubed plus x. I distribute that x through to get rid of those parentheses. Now, from the next step, I had to multiply, distribute that a through, so that's how I got ax to the fourth plus 2ax squared plus a. And then I had to multiply these two binomials, so x cubed times bx is b times x to the fourth. Then I did in descending order, c times x cubed is cx cubed, b times x is bx times x is bx squared. The next times c is cx. I think I've expanded it all out. And then, I could have, at this point, I could have collected my like terms, and that's really what I'm doing. But I'll try to explain that in the next slide. Clearing the denominator, now what I can do is I can match up all these terms with their corresponding part into the numerator. So I'm looking at I get a negative 10x to the fourth. Well, I've got an ax to the fourth, and I've got a bx to the fourth, and I don't have any other x to the fourth terms. So I know that a times x to the fourth plus b times x to the fourth has to equal negative 10. And then I know that, let's see, so what I've got for the x cubed term, which has a coefficient of 1 right there, right? There's a 1 right there, so I wrote that 1 there. I'm only seeing just this single cx to the third. So that's what I'm going to have, is I'm going to have cx to the third. And that's what I kept matching these up and lining them up. So what do I get? I'm going to make a mistake if I just try to wing it here. So I've got, let's see, I know the x squareds are negative 19. I've got a 2ax squared. I've got a plus a bx squared. And then I've got a dx squared. And I think that's all of them, right? I got a 2x squared, a bx squared, and a dx squared. Oh, and then I've got the linear term, the x term, and that has a coefficient of 1. And I'm seeing, where am I seeing here? I'm seeing cx, I'm seeing ex. So cx plus ex is going to have the c and the e are going to add up to 1. Maybe I should put the x to the fourth, x to the third, x squared, x. Maybe that'll help you out. And then for the constant term, I'm just seeing the a is the only term in here that doesn't have an x with it. So I know a has to equal the negative 10. So now what I've got to do is I've got to change, I've got a system of equations. It looks like I need to solve this. I'll need to have a system of 5 equations with 5 variables, because I certainly have a, b, c, D and E are 5 variables, so I'll need to have 5 equations to solve that, and I'm seeing 5 equations. So I'm going to put this into that form next. So what I did earlier is that's what I did. You see how I have the bx to the fourth right there? Let's see. So the bx to the fourth and the ax to the fourth, those that went up to the negative 10. And then the single cx to the third, and what I did is I had to make sure I added in, because I need to have 5 equations with 5 unknowns. I didn't have any c, d's, or e's in that first expression, so I just added zeros. And the same thing in the second line. I didn't have anything but the c, so I added zeros there, so on and so forth. And then I pulled the coefficients out of each of these equations into a matrix. So 1, 1, 0, 0, 0, and that's equal to negative 10 over there. And then I went 0, 0, 1, 0, 0, and that's the next row, 0, 0, 1, 0, 0. Okay, so that's how I got the matrix. And then I went to my calculator, and I don't know if you can see that very good with the glare of the lights. What I pressed was, let's see, second, x to the negative 1, and there's that matrix feature over that key, and that's how I got to this screen. And then you usually have the names being dark, and we want to have the edit. We want to be able to edit our equations. So I just hit the right arrow twice to edit it, and then I hit enter, and what that lets you change it to a 5 by 5 matrix, 5 rows, 5 columns. I entered these numbers in, and then I went back, quit this, went second matrix again, edit, and I edited matrix number 2, let 2B, and this is the 5 rows, 1 column, and I put that in matrix B. And then I let my calculator, I quit after I entered in all those matrices. I went second, I pressed second matrix, and I didn't edit. I just got the A matrix. And then the mathematics behind this is if you've never worked with matrices, or if it's been a long time, if I know A, think about it this way. If I have a number times X equals another number, the way you solve that simple equation, that one-step equation, is dividing by a, right? Well, the other way to solve, not divide by a, but multiply by 1 over a times a equals b times 1 over a. So, with matrix algebra, the way you find the inverse, or the reciprocal, it's called the inverse, is we hit the x to the negative 1 key. And that's how, same thing. What we've got is we've got this matrix equation. Maybe you better step back here. So I have matrix, the coefficient matrix, that big 5 by 5 matrix, times the variable matrix has to equal the constant matrix. In this case, where I put it in B. So you see how that's the same math. A times x equals B, A times x equals B, same math. So we're going to multiply by the inverse, and if I multiply by the inverse, those cancel out. So that leaves me the answer matrix is equal to the inverse matrix times the coefficient matrix. And the other thing you got to keep in mind about matrix algebra is I've got a 5 by 5 matrix, and I'm multiplying that by a 5 by 1 matrix. These two numbers have to be the same in order to multiply them. That's why I couldn't multiply this b times a inverse, because that would be a 5 times 1 by a 5 by 5, and these two numbers aren't the same, so I couldn't multiply those matrices. Okay. So, how do you get this answer now that the calculator did all that, solved that system of equations very quickly and easy? How do I put this back into a partial fraction form, or a fraction form? So do you remember how each of these fractions had an a, and this had a bx plus c, and this had a dx plus e? So the a is negative 10. The b is 0. So there, it doesn't even have to have that term there. The c is 1. That's why I wrote 1. The d is 1, so I wrote 1x or 1x. And the e is 0. And that's the partial fraction form. And I worked this out to check it. What I did is I just added these two by combining, getting like denominators. And it did work out and check, so I know I'm right. So I hope that helps. I mean, it's involved, but it's not impossible.